So we saw our first example of a general complex number, right? Minus 2 plus 2i, minus 2 minus 2i. We can combine anything that doesn't have an I plus anything else that has an I, and we get a complex number as well. So if we look at the set of everything that looks like a sum of a real number, A, plus a real number times the imaginary root I, then we get a set of sums, where one bit is a real bit and the other bit is a complex bit. You have to also be familiar with this notation. When we write something like this to describe a set, typically the bit here that comes before the vertical line tells us the form that the elements of the set have. And then the bit that's on the right tells us what the constraints or the restrictions on the parameters are. So sets often end up being written as, here's P given Q. P is the general form. Q is a set of constraints or restrictions. So this set here, C, is the set where every element has the form A plus BI, and the restrictions is that A and B are real numbers. You could add as a restriction that I squared is equal to minus 1, but that's also sort of implicit here. It's a given. When you take an element from the set C, C for complex numbers, you write it as A plus BI. The A, we have a name for it, it's the real part of Z. We'll see later that this corresponds to the horizontal coordinates. The B, not BI, the B, the coefficient in front of the I, that's the imaginary part of Z, and that is going to represent the vertical coordinate of a two-dimensional point. The real part and the imaginary part are real numbers. I want to repeat this. The imaginary part is not B times I, it is just B. When the real part is 0, when there isn't an A in your number, then you are left with something which we call purely imaginary. When the imaginary part of the complex number is 0, then what you're left with is a real number. So real numbers are a subset of complex numbers. Every single real number, pick your favorite real number. Let's say your favorite real number is pi. Pi is also a complex number. It's just not a purely imaginary number. It doesn't have any imaginary part to it, only a real part. But real numbers are complex numbers as well. It's a restriction of the complex numbers. You could write, if you wanted, that R, the set of real numbers, is the set of every complex number. So this is the form, and then the restriction is that the imaginary part of Z is 0. Form, restriction. Typically, we draw real numbers on the real line. Let's assume this is a line, it's not very straight, let's say it's a line. Horizontal line, 0 is here somewhere, and then for instance pi might be here, to the right of 0. And minus 10 might be here somewhere, a little further than pi. Well, it's not up to scale here, right? But that's sort of the idea. Complex numbers, not represented on the real line, they are represented in the complex plane. Horizontal axis is R, the vertical axis we might call I times R. Horizontal axis is the real part, Vertical axis is the imaginary, pure imaginary part. When you have a quadratic equation, or quadratic polynomial that you want to solve, ax squared plus bx plus c is equal to 0, you know by using the quadratic formula that the solutions are minus b plus or minus square root of b squared minus 4ac divided by 2a. The plus or minus is there because by convention, right, if we just have one square root, we've said that we're one square root sign, we're talking about one value, but the plus and the minus there, we're reminding you that there's two possible square roots here, and we in fact mean both square roots. Now, if that's the case, every quadratic polynomial has two roots. Any quadratic equation has two solutions. If it turns out that the discriminant is the bit underneath the square root here, sometimes is written as delta. If the discriminant is strictly positive, then the roots are real and they're distinct. If the discriminant is equal to 0, the roots are still real, right? Because you're taking the square root of a 0, which we know is 0, but they are identical. And so in that case, we think of the root, which is unique, as a double root. We count it twice. And if b squared minus 4ac is strictly negative, then the roots are complex because this little bit here is a negative number. You're taking the square root of a negative number. You will end up with imaginary terms in here, and they're distinct as well. So it's a little bit of a cop-out to say there's always two roots because you say, well, there's only one, but we count it twice. The argument for why we do this is steeped in continuity. So I'm not going to rehash it here, but when you talk about calculus, you'll see that very often limiting behavior is of interest to us, and we often want to preserve limiting behavior. And what's happening here is that as the discriminant gets smaller and smaller, the roots get closer and closer until they are right atop on one another, and then after that they disappear and go into the complex world. It's still two roots from our perspective, but it's, you know, they're not always going to be distinct. Two roots can be the same. How do we conduct algebra on the complex numbers? For a lot of things, the algebra on the complex numbers works exactly the same way as it does on the real numbers. Just you add one additional rule, I squared equals minus 1. There is one way, though, one glaring exception, in which algebra does not work the same way in C as it does in R. How can you tell if two numbers are equal, if two complex numbers are equal? It's easy. Their real parts have to be equal, and their imaginary parts have to be equal. How do you add two complex numbers together? Again, easy. Add the real parts together, then add the imaginary parts together. How do you multiply complex numbers together? No, this one is less easy. It's less obvious. Later, we'll see that multiplication is basically a rotation, and it will sort of make sense. At least this formula will make sense, but for now, you have to remember this formula by heart. The product of two complex numbers is this expression. You take the real part of the first number times the imaginary part, times the real part of the second number, minus the imaginary part of the first times the imaginary part of the second, and that gives you a real number. That is the real part of the product. And for the imaginary part, you take the real part of the first, multiply by the imaginary part of the second, plus the imaginary part of the first, multiplied by the real part of the second, and that gives you an imaginary part. It's like, well, okay, well, that's not obvious. We'll find a better way to describe products of complex numbers shortly. Like I said, rotations. But for now, there is a formula. This is something you have to remember. The way in which things differ fundamentally from the real numbers is that if you give me two complex numbers, let's say Z and W, it might not make sense for me to tell you that one is larger than the other. With real numbers, it always makes sense. Give me a real number. What's that? 17. Got it. Give me another number, minus pi. Well, I know that one is greater than the other, or potentially they're equal. But minus pi is smaller than 17. Now, if you give me two complex numbers, let's say 3 plus I, and potentially, I don't know, minus pi. Can't compare them. Cannot say that one is bigger than the other. And one thing I should mention about equality, addition, and multiplication, if you are restricting yourselves to the subset of the complex numbers, which is the real numbers. If the imaginary parts are 0, then equality, addition, and multiplication of complex numbers is exactly the same as equality, addition, and multiplication of real numbers, right? Because take multiplication, for instance. If B is 0, this is gone. And if D is 0, this is gone. And the product would just be A times C, which is AC. These things would disappear, B times D, because they, 0 times 0. And B is 0, this disappears as well, and you're left with AC. So when you restrict yourselves to the right subsets, the rules you're familiar with still apply. Division looks different, substantially more perhaps than multiplication does. But if you look at it in the right point of view, you'll see that division in C is basically the same as division in R. Let's take a quick look at this here. Let's say we try to solve 4 plus 3i times z equals 1. What does that mean? It means I want you to find the value of z, which is going to make it so that 4 plus 3i times z is 1. You can't, I mean, if these were real numbers here, you would just take the 4 plus 3i on the left and you divide the right-hand side by that. So in essence, this problem is asking you to find the value of z, which is 1 divided by 4 plus 3i. How do we solve that? How do we compute this quotient? We are going to use a specific trick, the trick that says that, look, I, if you remember, is actually a square root. Well, it's the square root of minus 1, but it is a square root. And when we have terms in the denominator that consists of sums of square roots, we suggest trying rationalizing the denominator. This is something else you remember, presumably from high school. How so? Well, if you were to take the complex number a plus bi, eventually for us a plus bi will be 4 plus 3i, but for now let's just not say we have specific values of a and b, just general values of a and b. If you multiply a plus bi by a minus bi, in other words, if you change the sign in front of the b, then what do you have? You do FOIL again on this thing, so a times a, that's a squared, a times minus bi, then you'll have bi times a, so you have a times minus bi plus bi times a. These terms cancel out. You get minus abi plus abi, you get 0. Incidentally, that was what was happening when we were finding the cubic roots, when we're trying to find solutions of cubic polynomials, right? There was a square root of a negative number, but it would cancel out because we also had minus the square root of that same number, and it disappeared. And finally, you end up with bi times minus bi. That gives you minus bi squared. Like, okay, so the product of a plus bi with a minus bi is simply a squared plus b squared. Well, why plus b squared? Bi squared would be b squared I squared, and I squared is minus 1, and minus 1 times minus 1 is 1. So we have a squared plus b squared, this expression right here. So when we multiply a complex number by this other complex number where the sign has changed, we call this the complex conjugate, then we get a very nice expression, a squared plus b squared, something that should remind you of the Pythagorean theorem. I don't know how to say that name in English. Pythagore, at any rate. Now, if a and b, the real part and the imaginary part of the original number, are not equal to 0, we will have that a squared plus b squared is not equal to 0. And when I say that a and b are not equal to 0, what I mean here is that as long as one of them is not equal to 0, then the sum a squared plus b squared is going to be different from 0. But more than that, we know that it's going to be greater than 0, because a squared plus b squared cannot be negative. A is a real number, b is a real number, a squared is positive and or 0, b squared is positive and or 0. So the sum of these two things together would be at the very least non-negative, and as long as one of a or b is non-zero, then a squared plus b squared will be strictly positive. When you look at what we've just done here, you can use specific notation, right? If you write a plus bi as z, z bar is the number you obtain from z when you replace the sign here by the other sign. So replacing a positive by a negative, or potentially a negative by a positive. We call that the complex conjugate. And the result of that computation would be the square of the modulus, the square of the absolute value of the complex number. So what we've discovered, if you want, by explicitly writing out the product, is that z times z conjugate is the square of the modulus of z. And we know, again, specifically, that if z is not the complex number 0, meaning that it has at least a real part or an imaginary part that are different from 0, then the modulus of z is itself going to be not 0. So if both a and b are 0, then the modulus will be 0. Right? These are basically the same statement. If you use this notation, as I said, z times the conjugate of z would be the modulus of the or the square of the absolute value of z. And so you can rewrite this, right? I'm going to take the absolute value of z squared, and I'm going to divide both sides of that by this quantity. So here I get z times z bar divided by absolute value of z squared, and here I get divided by absolute value of z squared. And assuming that z is not equal to 0, then I can do this because I'm dividing by something which is different from 0. This becomes 1. And so z bar divided by the absolute value of z squared gives me 1. If I wanted to, I can go even further, right? I'm going to take the z, which is right here, and I'm going to divide it on both sides. So let me divide by 1 over z here, or multiply by 1 over z, I should say, and here also multiply by 1 over z. These z's cancel out, and here we just get 1 over z. So that gives us 1 over z is equal to, I'm just going to rewrite here what we had because it got lost underneath all of these things. That would be the conjugate of z. Also, sometimes I'll just say z bar because it's easier to say, divided by the square of the modulus. So 1 over z is what I'm looking for, and I get it by finding the conjugate and dividing by the square of the modulus. What does that look like in terms of the real part and the imaginary part? 1 over a plus bi, 1 over z, that's equal to z bar divided by the square of the absolute value of z. That is a minus bi divided by a squared plus b squared. These are all quantities we found on the previous page. So 1 over 4 plus 3i, which I remind you was the thing we were actually interested in. Now we're going to replace the value of z by the specific complex number 4 plus 3i. A is equal to 4, b is equal to 3. I just reuse the formula. So that gives you 4 minus 3i divided by the real part squared plus the imaginary part squared. So 4 squared plus 3 squared. 3 squared. So 4 minus 3i divided by 25, which you can simplify further as 4 over 25 minus 3 over 25 times I. Is there one of these answers which is best? No. I mean, the only time that you might need to simplify things for real, unless you're specifically asked to simplify, is if you have a multiple choice question and you have to recognize which of these possible answers is your answer. It's never a bad idea to separate the real terms, the real parts and the imaginary parts, but it's not always necessary, right? Unless you want to recognize one of the answers from a list of potential answers, or unless you're asked to do it specifically. All right, so we saw how to divide 1 by a complex number z. What if we don't want to divide 1 by z? What if we want to divide a complex number by another complex number? Here we use an old trick, and that trick is to multiply by 1. But the thing is, we're going to try to find a very specific way to write 1. We often use tricks like this: multiply by 1, but use a judicious choice of 1. Sometimes you add 0, but you write 0 in a clever way that simplifies things. You'll see that in calculus when you compute the derivative of a product, for instance, in the definition, I mean. Now, we're going to write 1 as w bar divided by w bar, where w is actually the denominator here, the thing we're trying to divide by. Now, in this case specifically, w is minus 2 plus 4i, so the conjugate of that would be minus 2 minus 4i. And so I write 1 as minus 2 minus 4i divided by minus 2 minus 4i. And that's true, like minus 2 minus 4i divided by minus 2 minus 4i is equal to 1. But why this? Why didn't I write 1 as 3 divided by 3? Or like, pick my favorite number, 17 plus pi I divided by 17 plus pi I. Why not? Well, there's a reason for that, is we're going to try to basically rationalize the denominator, right? It's the same trick we were using before. So if we do that, if we have that specific choice, the quotient that interests us, the division of these two numbers, take that and multiply it by 1. But you're going to multiply it by the special one which is written here. So you'll rewrite 1 as minus 2 minus 4i divided by minus 2 minus 4i. The nice thing about this is that these two denominators, when you do FOIL on them, you're going to get back to this expression, which would be minus 2 squared plus minus 4 squared. And that gives you 20, right? This thing here, this 20, that is simply the square of the modulus of the denominator. And that's the reason why we do this. Like, we do not want to have things like this in the denominator. We don't know how to deal with this. We're okay having a sum of a real part and an imaginary part in the numerator, because that's literally how things are defined. That's how complex numbers are defined. It's the denominator that is problematic for us. If we rationalize, if we write 1 in a very specific way and take it from there, then we have exactly what we want. Then you just take the time to do FOIL on everything. I've hand-waved the fact that the FOIL on minus 2 plus 4i, minus 2 minus 4i will give you 20. Take the time to do it fully, but you see here that the terms that contain only an I will cancel out, and the terms that contain I squared, well, there's only one, the term that contains I squared, and you can just write I squared as minus 1, and you'll be able to get, 4 plus 16, 20. That's great. Now for the other numerator, you do FOIL again. 3 times minus 2 plus 3 times minus 4i plus 2i times minus 2 plus 2i times minus 4i. You do FOIL, you work it out, you will get 2 minus 16i, which, divided by 20, you can break down as 1 over 10 minus 4/5 of I. And that's a form that we recognize as a complex number because the way we've defined our complex numbers, I remind you, everything looks like this. And that here is clearly a complex number. It's clearly in that set. There's tons of easy properties here. Complex numbers satisfy a bunch of these conditions. I don't remember them explicitly, but I sort of know that they behave nicely with respect to the product and division. Same thing with the conjugate numbers and the modulus. The one that's very useful would be this one here, the triangle inequality. The modulus of z plus w is less than or equal to the modulus of z plus w. This thing here, I'm ashamed to say I never remember it. But I can always work it out because I do remember, as you should presumably, that z times z conjugate is equal to this one. If you know that one, if you remember this one, it's easy to derive the other one. So all these rules tell you really is that whenever you, tells you how to manipulate complex numbers, which is something, but whenever you encounter a z bar in an expression, what you have to do is to replace every occurrence of I in the expression for z by a minus I. If you do that, you'll be able to get what you want. I'm just going to prove 2 of these results here, and I'm not even going to be proving them out loud. I'm going to show you the slides. I'm going to let you read them. You can pause the video if you want. There's a lot of these results there, and they're not easy, or they're not always easy to prove. If you try to prove all of them, and by proving I mean try to show beyond the shadow of a doubt that the statement is correct, then you can use that result because you have proven that it is true. I'd say about 80% of the time in this course, when we present a theorem, a result, a lemma, a proposition, we will prove it. Before it is proven, we can't technically use it. It's like, it looks like it would be real. It looks like it would be true. This is a shortcut I should be able to use. Until you've proven it, you don't know that you can use it. You can say, well, somebody else proved it for me. It's like, well, that's probably good enough in the real world, or whatever the real world would be when we're talking about mathematics. But part of what we're doing in this course is to help you get a sense for why the things that people tell you are true are actually true. So we're going to have to do some proofs. That cannot be helped. So pause the video, take a look at the proof for the second statement, that the conjugate of a sum is the sum of the conjugates. When you're done, we'll look at the 10th statement, which tells us that the modulus of the conjugate is the same as the modulus of the number in the first place. You'll see in the proof of the 10th statement that it uses some of the statements of the lemma that haven't been proven. For instance, that the conjugate of z is the same thing as z. In general, let me rephrase that. In general, proving statement is something that we want you to know how to do because it shows you why something is true, other than somebody told me that it was true. If you're able to prove that something is true yourself, then you're less likely to forget the statement. Potentially, you're less likely to make mistakes when you remember it. Having said that, I pointed out an example where I never remember until I work it out myself. This thing here. We're not expecting you to be robots and to be able to remember everything by heart. But there's a few basic facts and results that you should remember from which you can derive a lot of the other results. Just in an examination, you don't always have a lot of time to derive the results that you want to use. So there is a non-negligible amount of memorization in this course. But if you just memorize for the purpose of memorizing, as opposed to memorizing things that help you better understand, then you're not doing this properly. I've mentioned complex numbers are best represented in the plane, the complex plane. This is one way in which you can represent this. The real axis is the horizontal axis, the imaginary axis is the vertical axis, and a point is, a complex number I should say, is a point somewhere. So for instance, this point here is the complex number z, which we've written as 3 plus 4i, and what it means is that the real coordinate is 3 and the imaginary coordinate is 4, so that you get 4i. Now, perhaps it's a misnomer to have the I in here, right? The imaginary component, the imaginary axis is just a real line that happens to be at a 90-degree angle from the other real line that is here. But sometimes we abuse the notation a little bit and we write 4i. What we're saying is that the point here is the point 4i, not that this distance is 4i, just as the point here is 3. So this distance is 3. This distance here is 4, not 4i. So we write z, the complex number is a plus bi. Z is the point in that plane. And when we have explicitly made it so that the vertical axis is imaginary, then we think of it as the complex plane, not just a plane. How do you add two complex numbers together? You add them the same way you would add two vectors. So you'd think of 3 plus 4i as a vector here. And then 2 minus 3i would be this other vector, slightly different orientation. And the sum of these two vectors would be, well, this one minus this one here, right? So I put it back here. I just translated this vector back here. And that new point right here would be the sum of 3 plus 4i plus minus 2 minus 3i. So complex numbers, the rule of addition basically says you add them as you would add vectors in the plane. Negation of a complex number is the negation of the corresponding vector, a reflection through the origin. If you multiply a complex number by a scalar, by a real number, then that has the effect of stretching or shrinking your vector. And multiplication by another complex number would have the effect of combining a rotation and some scaling in ways that we're going to discuss shortly. The conjugation operation, going from z to z bar, reflects a vector into the real line. So if this is 3 plus 4i, right here, 3 minus 4i is the point which is the reflection of 3 plus 4i in the real axis, right? Reflect this to this one there. There is no equivalent operation of reflecting in the imaginary axis. I mean, you can reflect in the imaginary axis, which would mean that you just change the sign of the real part, but that doesn't really give us anything useful. The modulus of z, that's the length of the vector. So if this is a vector or the complex number 3 plus 4i, there is a vector here, and the modulus of z would be this length. And because of the way this is set up, we always end up with a right angle triangle. Of A and B are the sides, and so the hypotenuse of that triangle would be the square root of a squared plus b squared, according to the famous theorem that tells us how to relate the length of the hypotenuse to the lengths of the sides. A lot of what we do might be easier to understand from a geometric perspective. And there's often a link between algebra and geometry that way. We define things from an algebraic perspective. Turns out that there's a geometrical view that allows us to better understand what we were trying to understand. That's often the case in mathematics.